Here's a problem that involves two train cars that are coming together and connecting with one another. Two rail cars with masses ma is equal to 15 megagrams and mb is equal to 12 megagrams, and the velocities are shown. We're tasked to find the speed of the cars after they meet and connect, as well as to find the average impulsive force between the two cars if the coupling takes place over a period of time of 0.8 seconds. So as always, we start by writing down what's provided by this problem. And so we're given the masses of the two objects. So when I write what is given here, I know that mass A is 15,000 kilograms. And I know the mass of object B is equal to 12,000 kilograms. In this case, I know that the speed of object A is 1.5 meters per second, and that's towards the right, and the speed of object B is 0.75 meters per second, and that's pointing towards the left, like so. Okay, so what is it that we're trying to find? We're trying to find the speed, the final speed of the two cars. So I'm just going to call that V2 because they end up connecting with one another. So they move together with a common speed. So I can just use one variable, call it V2 to describe that. And we also need to determine the average impulsive force that acts during this impact between the two objects as they come together. So the first trick here is to recognize that, well, we're dealing with a collision of sorts, and for a collision or for an impact, we know that the total momentum is always conserved. This is true whether this is an elastic collision, a plastic collision, an inelastic collision. We know that the conservation of linear momentum holds for all impacts that we study in this class. And so if we consider one state where object A and object B have yet to run into one another, so object A is moving towards the right, object B is moving towards the left, this would be our initial state. And then our final state is going to be where they finally collide with one another, and then they move together with some common velocity. Now, I don't know which direction it's going to move in, but I'm going to say they happen to move to the right. That's my guess. If I'm wrong, I'll find that that final velocity v is a negative based off of the equations that I use. Now, we have to remember that momentum is a vector, which means that it's very important for us to describe the positive direction so that we can determine whether an object has positive momentum or negative momentum. The same thing with, say, a force or a velocity or acceleration or any other sort of quantity that is a vector. We need to be able to specify the direction in addition to its magnitude. So the conservation of linear momentum says that the total momentum before the collision will be equal to the total momentum after the collision. So the sum total of mass times velocity, we'll put this in general terms, so we'll put the arrow over velocity, before the collision is going to equal to the sum total of momenta after the collision. So the subscript I indicates over all particles that we're considering. It's kind of funny to think that trains can be modeled as particles, but if we only concern ourselves with the centers of mass of these two objects, then it's totally valid to model these large objects as particles, which we generally think of as being just no defined shape, but of a specified mass. Anyway, recognizing that all of the motion occurs along this x-axis that we've described previously from our diagram, we only can use the x direction linear momentum equation to really yield anything meaningful from this problem. So if we write out in the x direction the conservation of momentum, we find that the initial mass times velocity in the x direction of object A plus the initial mass times velocity in the x direction of object B, so we have to put these subscript 1s here, is going to be equal to the total momentum of object A and object B after the collision has occurred. And they tell us that the two cars meet and connect. This is actually very important. This indicates that we have a plastic collision situation here, where the objects actually connect with one another. If we were to invoke the coefficient of restitution, we would find out that the coefficient of restitution for this scenario would be where E is equal to 0 in this case. That corresponds to a plastic collision. The two objects meet, combine, and then shuffle off at a new final velocity. So with that being said, the final momentum, which is what we consider for the right-hand side of this equation, will be the sum total of the object's masses, mass A plus mass B, times their combined final speed, v2. Now we have written this linear conservation of momentum equation in the x direction. This was initially a vector equation, but vector equations are beautiful. We get three scalar equations for the price of one. In this case, we only chose to use the x direction, but we still need to obey this sign convention that we've outlined for ourselves in the previous slide. X is positive to the right. So initially, the mass of object A, this is 15,000 kilograms. We use kilograms, that's our base mass unit in the SI units, times 1.5 meters per second. Okay, that's positive because it's moving towards the right, plus the mass of object B, this is 12,000 kilograms, times its velocity is 0.75, but we put a negative sign in front of it because it's moving towards the left, meters per second, and that's equal to the sum total of their masses, 15,000 plus 12,000. This will be in units of kilograms, times V2. So V2, when we solve for this equation, is going to be in meters per second due to our dimensional analysis that we've performed by explicitly writing out the units in our equation. So when there's one equation, one unknown, we simply had to solve for the final speed. V2 is a positive 0.5 meters per second. Okay, so the fact that it's a positive 0.5 meters per second indicates that the choice of that final velocity V2, which is positive to the right, was the proper choice. Now, if I had drawn it to the left, I would have put a negative V2 into my equation here, and I would have found out that V2 was a negative 0.5. That doesn't mean that it's pointing in the negative direction. It just means that the velocity direction that I had chosen for my diagram was opposite the actual velocity that the cars were moving in. Okay. The next part of this question asks us to determine the average impulsive force between the cars, assuming that the coupling process takes place over a period of time of 0.8 seconds. Well, in order to uncover information about that impulsive force, let's take a look at what's going on from object A's perspective. Well, initially, object A is traveling along with some linear momentum, MAVA1. We know all about this because we know its mass and we know its initial velocity. Then, all of a sudden, it feels an external, from its perspective, an external impulsive force that's due to object B, and this is pointing in towards the left. This is the direction of the force that it feels from object B. It's feeling towards the left. So the impulse it feels would be this impulsive force F dt over a period of time t1 to t2. And that's going to yield a new situation where the object, well, we know it's going to move off to the right still, MA, it's going to be traveling at speed v2 of 0.5 meters per second. We just solved for this. Okay. This is a graphical depiction of the linear impulse momentum equation. It says that in this case, mass times velocity 1 in the x direction plus the sum total of all impulsive forces, okay, the sum total of all impulses, I should say, from period t1 to t2 is going to equal a new mass times velocity, or simply put, a new momentum. The only way that you can change an object's momentum is if you apply an impulsive force, a net impulsive force on this object. It's very similar to the work in energy principle that says that an object will have kinetic energy and will maintain that kinetic energy until a net amount of work is done on that object. the linear impulse momentum equation says that an object will have some momentum, and it will continue to have that momentum until a net impulse, external impulse, acts on that object. So again, we recognize the only unknown in this equation will be the force, because we know the mass of the object is 15,000 kilograms. We know that it's moving to the right at 1.5 meters per second initially. This is still a vector equation. It's written in the x direction, but it's fundamentally comes from a vector equation. We need to obey the positive and negative sign conventions, which are still described by our original diagram, positive x being towards the right. So our initial momentum is 15,000 kilograms times a positive 1.5 meters per second, plus, well, there's only one force, external impulsive force, that it feels in the x direction. So this takes place over a period from 0 to 0.8 seconds of some average force. So this is a constant force, dt, and that's going to yield a new momentum, which is still the same mass, 15,000 kilograms, times its new speed, which we solved for previously is 0.5 meters per second. Again, this is positive because we determined that the two objects shuffle off together towards the right, which is the positive direction. So solving for this, we recognize that bringing 15,000 times 1.5, subtracting that from the right-hand side, 15,000 times 1.5, we're left with, well, on the left-hand side, we still have 0 to 0.8 of our average force. I'm going to pull that out of the integral because we recognize that's a constant, dt. And if we subtract the 15,000 times 1.5 from the 15,000 times 0.5, we recognize that that's going to be equal to a negative 15,000 times kilograms times 1 meter per second. Okay, when we subtract that value out, okay, so that negative is important for us. So F average, we perform this integral, that becomes t, evaluated from 0.8 and from 0, that will be 0.8 minus 0, okay, is equal to negative 15,000 kilogram meters per second. And so that allows us to solve for our average impulsive force, which turns out to be negative 18,700 newtons. It's negative because it's pointing in the negative direction. Okay? And the way I set up this equation is I actually added my force. I included this plus sign here. So by including that plus sign, I inherently assumed the force was pointing in the opposite direction from how I drew it on my diagram. And so when I found out that my average force was a negative quantity, well, that agrees with how I had drawn my diagram because I had pointed it in the negative direction. So the fact that I had assumed it positive with my equation and it found out to be negative means that, yes, in fact, it was pointing in the opposite direction, which is in the negative direction. So this was absolutely correct. The magnitude is still 18,700 newtons, pointing towards the left.